plus 15.
You got 1 over 8s?
Well, 8 squared
S squared.
plus 8s
8s
plus 15.
plus 15. Okay, everybody's gonna get something slightly different, okay? Marquez, you get to get the exact solution everybody else.
It was supposed to be me.
Alright.
Can we use those numbers?
Huh?
When we submit it to you, is it alright if we use those numbers? Drop them on.
Yes. Yeah, that's fine. You can use these numbers. Alright, what do we got? Part A. Pole 0 map. Okay, so what are my poles?
-3, -5.
How do you know that?
I found it.
You gotta factor it?
Yeah.
And I think I gave everybody nice numbers, right?
Yeah.
Is that correct? Did I give everybody nice numbers? I did? Okay. So everybody should be able to factor just fine. So just by looking at the poles, what kind of system is this? Second order? Overdamp?
Overdamp.
2 real?
Overdamp.
Overdamp? Okay, cool. Alright, what are my zeros?
None. There aren't any.
There are none. Okay, so if I draw my pole 0 map, what do I look like?
Yes, you will be making something real.
Is this stable?
Yeah.
How do you know?
Negative.
They're all in the left-hand plane. Perfect. Is that part A?
Yep.
All right. Part B.
Find omega n, zeta, and ts.
Find omega n, zeta, and
Ts, the settling
the
time.
settling time. Okay? So how do you get omega n?
Square root of K, right?
Well, there is no k around.
It's,
I think square root of 15.
Square root of 15, right? This is omega n squared, right? Because what does the general form look like? 1 over, oh, actually, it's omega in the numerator, right? 2 zeta omega n plus omega n squared. That's the general form. So omega n is square root of 15. That's not so nice of a number, but just leave it. All right? Okay, how do you find theta? There you go. So just do 2 zeta omega n, which we know is square root of 15, equals what? 8. Okay, so then you get zeta is 4 over 15. Square root of 15. Okay, again, I don't know exactly what that is. Is that greater than 1?
Yeah.
How do you know?
I've just put in my calculator. It's like
Square
1.02.
root of 15 is 4.
Because, yeah, okay, square root of 15 is less than 4. How else do you know that zeta is greater than 1?
It's over down.
It's over damn. Nice, good job.
No, I just did it.
You're not going to have a calculator on your test.
One moment. Okay, I mean, I just found out. Is that answer just?
But you can just leave it as 4 over square root of 15.
Here we go. You know, we're just done.
What's going on?
Something funny was on it.
Oh, okay.
I just read one of your comments.
Oh, okay. Oh, you read one of my comments?
Yes, I put between ish on there.
Oh, okay. I think Ish was not your friend. So
Yep.
yeah. All right, and then TS is what? 4 over zeta omega n? There is no need to plug these two in because the square root of 15 is going to cancel. Don't do that. Okay? Just plug in this number, which is just 4. So it's going to be 4 over 8 over 4, right? Did I do that right? No, 8 over 2. Is that right? Somebody verify.
Yeah. That's right.
So then I get just 1, right? So I get a settling time of 1 in this case. Cool? Yes, no, maybe so? Yes. Okay, all right. Is that it? Part B?
Yeah.
Okay, part C. What do we got? General form of what? Time response, okay? X of t equals what for a step?
E to the negative 3, 2. I mean, A plus B e to the negative 3, 2. Plus C e to the negative 5, 2.
Why is there no t there?
Because it's not repeating.
It's not repeating, right? Yeah, it's just, yeah. Okay, that was it, right? Okay. Part D? Unity step input plotted. So I really just need to plot this. But I told you something that you needed to do. You needed to mark two things on the graph.
Peak time and
Not necessarily your peak time, because this is a overdamped system, so there is no peak.
What's your maximum settling time?
Yeah, I want the asymptote, so I want this guy, and I want your settling time. So we know what the settling time was. What is it? 1. What's my amplitude? It's not A. I can actually compute this.
Wait, why isn't it
Huh?
A? Why isn't it
It is a,
It is A, but I want a number.
Oh, okay.
Yeah.
partial fraction.
Yeah, let's do this the long way, just so you see where it's coming
Oh, wait,
from.
you couldn't just say A?
No, I didn't want A. I wanted a number. Yeah, it's dumb, isn't it? I took off 25 points for that.
Yeah, you did.
Yeah, we're getting to that. Well, let's do it out the long way so everybody knows where it comes from. Okay. So if you partial fractioned this guy, say this was hit with a step. So I'm going to put x is s. Is s times all this. How would you partial fraction that?
1 over
A
S.
over S
A over s.
plus B over S. D, yeah, all that, yeah, there you go. That's what I was saying.
Okay, all of this doesn't matter, right? This is just going to be stuffs, right? I don't really care. I don't really care. And actually, you can factor this into this, right? So actually, we should probably do this then.
B over S.
Yeah, it'll be b over s plus 3 plus c over s plus 5, right? You can actually do that if you wanted to. All right, but again, I don't care what b and c are. I care what a is, right? Well, if I cross multiply, I get 1 equals what? A times,
S plus B, S plus 5.
yeah, s squared plus 8s plus 15. I get b times what?
S, S plus 5.
And then c times,
S plus 3.
okay, so if I only want to solve for a, what do I do?
Substitute S equals 0.
Just plug in s equals 0. How do you know that? Huh? I can, huh?
You can see it if you plug in 0 for S.
Yeah, but how do you know you can see it?
Because B and C go to 0.
There you go. Okay, so because b and c go to 0, right? So b and c go to 0 because there's an s there. So if I plug in s equals 0, I get 1 equals 8a times 15. All this drops out, so a is 1 over 15. Okay? Now, what is this actually equal to? This is equal to the numerator divided by omega n squared, right? So you could do this the long way if you wanted to, and I wanted to show you that just so you know where it comes from. But it's really, really simple to just look at it like this and say it's the numerator divided by omega n squared. So if I took the shortcut, I would just take the numerator and divide it by omega n squared. There's a. Done. Or you could partial fraction it, just the long way. Are we going too fast?
That was nice. If you have an S in the numerator. That sucks. You have it long way. You know what I'm saying?
Yeah, right? Because then you would have, like if you had one s, you would get an s here, right? If you plugged in s equals 0, a would be 0, wouldn't it? No, but then this s would cancel with this s. You know?
I just wanted to like something like. There could be a situation where your numerator has an S and it doesn't work, right?
I'll think about it later. I'm not going to put something like that on your test though. I mean, like your final project, right, had an s in the numerator,
That's what
but you just converted it to state space anyway, because I like state space better.
You also have an
Joshua?
S. You have an S on your C.
Yeah.
Is that supposed to be there?
Yeah, because I cross multiply by this entire term. So I get an s, the s plus 5 is cancel, I get an s plus 3. Does that make sense?
And it's gonna like curve towards that one.
I got a lot of cross chatter. You guys have any questions? Okay, should we move on then, or?
So it curves towards the,
Yeah, so now we have to plot it, right? So what is the shape gonna look like? Is there gonna be any overshoot?
no.
How do you know?
This is over.
It's over down. So it's just gonna do this. Close enough. If you drew overshoot, I took off points. If you drew something that looked like that, I gave it to you. I wanted a number there, though. What did we just do here? What is this called? What kind of time response? Open loop step response. There you go. Yeah. What we're doing is we're looking at the open loop step response of the system. Good job. All right. You want to move on to part E? All right, what's part E? Block diagram. Did I say that, I think I said U equals KPE plus KDE dot. Okay? If I took the Laplace transform of that, what would I get? Big U equals KP big E plus KD. How do you take the Laplace transform of E dot? S what? S big E. So I'm going to pull out big E. And I get that. Okay? How does that look? All right, so if I write this in block diagram form, I'm going to put my plant here at G. I said there was unity feedback, right?
Yes.
So I know that my output is going to be Y, and I'm going to feed that back. I said it was unity, right? So there's no sensor. Yes?
Correct.
And then I'm going to bring this up, and I'm going to compare it to some input, right? Say R. What is my input into G?
E.
Not quite. Error is actually the output of this summing block.
Oh,
Error,
G, yeah.
yeah, error is the difference between R and Y. Yeah, the input here is U. And what does U equal in relation to E? That formula. So I could write that as one block. I'm going to get a little bit fancy. And I'm going to split E into a KP block. I'm going to put a summing junction here. And I'm going to put another block here called KD. That's too small. So I'm going to draw it like that, just so we see where everything comes from. Okay? If you left E inside these blocks, and when you reduce down your block diagram and you had E in the numerator, that's not quite right. E is a signal and it's multiplied by this block. The actual transfer function block is this term, and that gets thrown into here. Okay? So that's an important thing I think a lot of you miss. So this is PD control. Is that too small? Trevor? Well, Trevor, what about you? You good? All right, that was part E. I tried to give you points for, getting like the output, the transfer function, the unity feedback, so on and so forth. So there were a lot of like 40s and 60s and 80s.
What's that thing by the U? Is that using summation block?
Yeah, that's a summation block. So you take KP and KDS and you add them together. What is this in? This is cascade, parallel, unity feedback, parallel, and then these are in cascade, and then this guy, unity feedback. So when you reduce this block diagram down to one, you have to use all three special cases, right? You guys ready for part F? Yeah? Okay. So what's part F? How do we do it? Convert it to a single block. Okay, so what are you going to do first? Yeah, combine the parallel. So that one's not too bad, right? What do? You just add them, right? So you might have just skipped this step because you might have just left this as one block as it is already. But yeah, these will just come together, and this will be KP plus KDS. And then what do? Cascade. So then you'll pull these guys together. Let me draw this in a different color. And I actually know what G is, so I'm just going to multiply that in. I'm going to get KP plus KDS over S squared plus 8S plus 15. Okay? And then what do I do? Huh? Feedback. And what's the formula for feedback?
G over 1 plus H.
G over 1 plus G, because there's no H, right? But if there was an H, I would have an H here, right? Say what?
I was just trying to.
Yeah. Is there an H up here? Or, no? This is one. It's G over 1 plus GH. Okay. All right. Yeah. So H is 1. So it's a G over 1 plus G. So I always like doing this the long way, even though it always works out the same. KP plus KDS all over S squared plus 8S plus 15 times 1 over 1 plus KP plus KDS. And then you pull this guy into this guy. This one cancels, and you just end up getting KP plus 15 and then KD plus 8S.
Can we always assume that H is 1?
No, you cannot.
Then why are we assuming
Good,
that?
H right there.
Because I gave it to you in the problem.
You did.
Yeah. H is 1 here, but on your final I could easily put a block here and then it wouldn't be 1, right?
Oh, no.
Yeah, so expect an H in there. Alright, so I get S squared plus 8 plus KD S plus KT plus 15. There's your single block. Cool? You guys ready for the next part, or not yet? Not yet?
So the actual, it's not our block.
Yeah, so if we want to draw it in block diagram form, our single block would be R KP plus KD S There you go. How about that? Oh, and then output is Y. How about that? Ready? All right. Part F? Or was that part F? so this problem was really, really open-ended. What's the general form of that? Depends on what KP and KD are, right? So you could say, I'm going to get something that looks like, you know, KP plus KD S over S squared plus 2 zeta omega n plus omega n squared. I am going to get something like that, right? And what's again, still, yeah, depending on what KP and KD are, you're going to get something different. Now, depending on what zeta and omega n are, you're going to get something different as well, right? So basically, anything you write is pretty much going to be okay. Stefan?
The second term is denominator.
Yeah. So what would you write?
I left it blank.
You left it blank.
And then we'll just put C over R equals TS equals K plus K.
I mean, I want a time response equation.
You could say A plus B cosine, excuse me, B e to the negative zeta omega n cosine of omega d minus B.
That's right. That's a acceptable answer. What would be another acceptable answer?
This is a general form, right?
That is the general form. What else could you put?
Could you do like the b e to the negative t and do like the other term c or d?
You do this, and what is S1, S2?
Oh.
There's a zeta in there, isn't there?
You say omega d, right? Plus or minus omega d.
Yeah, you can do plus or minus omega d. But what is omega d?
1 minus d squared or something.
Omega n squared 1 minus zeta squared.
There we go, that's what it is. I can get rid of the I. There you go. You could write something like that. I think either of those are fine. Does that make sense? The second one makes sense?
To me.
Okay. Dylan?
So this whole block diagram is addressing unity feedback with proportional control.
That is unity feedback with PD control.
PD control.
Yes.
Because you don't have a KI in the equation.
You don't have a KI in the equation, exactly.
With proportional control.
PD.
PD.
You can put either of those extra T's.
Yeah, either one.
Or specified information from
If you don't know what KP and KD are.
I mean, it's real general.
Super general. Yeah. This is probably the most general, but this is fine. Okay, so now the big tamale, right? Part H. You're still writing? Fine.
They do the quadratic formula, right?
That's what I did. Some people did Ralph Hurwitz though. Huh? Yay.
I like Ralph Hurwitz for some reason. It's long-winded, but it works.
It still works. Yeah, it's fine.
If you like cutting or something.
Damn.
How did you like that? I'll do it right now.
Oh, yeah.
That was rough, sorry.
A little rough, yeah.
All right, stop. I need to say it.
All right, let's move on to part H.
I don't have the proportional control now.
All right. For root locus, the only thing that matters is your characteristic equation. The numerator doesn't matter. Okay. So my characteristic equation is s squared plus 8 plus kd s plus 15 plus kp. This is the only thing that matters. This is going to draw your root locus. Okay. What is a root locus?
Sure. Imaginary real is a plot on it, right? Like a
So
graph.
what are you plotting?
The real and imaginary parts of.
Real and imaginary parts of, hang on. It's a root locus plot where you're plotting on an imaginary real axis. And what are you plotting? The roots of the pole position, exactly. So the poles are going to change as you change Kp and Kd, and it's going to move your poles around the real imaginary axis, and you're going to make a plot of that. You guys got a question? You got it? You got it? Okay. All right, so part I said what? Plot the root locus of...
Well, wait, just pick H.
Oh, my bad. I don't know how to spell.
Vary KP with KD 0.
Okay, so Kd is 0, and vary Kp. So then basically my characteristic equation reduces down to this. Right? Kd goes away. And you want to make a root locus with this. Okay? We know already that when Kp is 0, my roots are -3 and -5. Right? Okay, so how do I make a plot of this?
You start increasing KP.
Yeah, you could start increasing Kp.
Find zeta at 1, 0, and various points.
You could do that, yeah. So you could find where this, you could complete the square, right? And find where it's here. And then you could find where it splits. What's another way to do it? And then you could try and plug in a couple points and connect the dots.
Quadratic formula.
I like the quadratic formula idea. So you would get -4 plus or minus square root of 64 minus 4 times 15 plus Kp all over 2, right?
How'd you get the -4?
Negative b over 2. Huh? Cool? Yeah? No? You got it?
Why is it B over 2?
Negative b plus or minus square root of b squared minus 4ac all over 2, and I just pulled the 2 over.
Oh,
I just split the 2. I split the 2 into 2.
can't do that.
I'm sorry. Well, I mean, I'll do that to you guys.
Yeah, algebra.
There you go. Yeah, the algebra, right? Okay, so with this, now we can try some of these fancy things that you're talking about, right? So how do I make this guy go here? What do I have to do to this thing to get my 2 repeated roots?
Set the square root to 0.
Make the square root 0, right? So I need 4, 15 plus Kp to equal 64. So what's 64 over 4? Let's just do this a long way. I need 64 minus 4, 15 plus Kp to be 0, and this will give me a repeated root. Repeated root. Okay? So I get 64 over 4 equals 15 plus Kp. What's 64 over 4?
16.
Is it 16? 16 minus 15 equals Kp. So when Kp is 1, I get a repeated root. Is that right?
Yeah.
Okay, so that means I can write here, I get a repeated root. Here is Kp equal to 1. Here is Kp equal to 0. And so that means I know that my roots are going this way. Cool? Okay, this one's an easy root locus. If I make Kp greater than 1, what happens? They're just going to go straight up and down. How do you know it's straight up and down and not curved?
Because the real side of your root stays the same.
The real side of the root is always going to be -4, right? Do you guys see that?
Yeah.
So if you change this, and this goes imaginary, you're just going to go straight up, okay? If you want to do it the long way, what could you do? If you want to make sure, what could you do? Plug in Kp equals something greater than 1. Give me a number greater than 1. 2. Okay, let's plug in Kp equals 2. Okay, Kp equals 2. So I get -4. I did the 8 over 4 thing, don't freak out. Over square root of 64 minus 4. 15 plus 2 is 17. All over 2. What's 4 times 17? Wait. 68. So I get negative 4 plus or minus 1/2 square root of 64 minus 68. What is that? So negative 2i over 2 plus or minus. So there you go. So I get negative 4 plus or minus I. So I get this guy and this guy. And so this is when Kp equals 2. So again, my pole did this and this. So what happens when I make Kp even bigger? They're just going to keep going. So my root locus looks like this. Boom, and then boom. Can I ever make this system go unstable by making Kp bigger? No, that's actually kind of cool. So I don't have to worry about Kp. I can make Kp as big as I want. I mean, I have to worry about saturation in the controller, sure.
Make KP negative.
Yeah, but how could you make this system unstable? Oh, no, that's too complicated. Yeah, you can make Kp negative. If you make Kp negative, your poles would do this, and then sooner or later you would cross. So this is Kp less than 0. But why would you ever do that? Now, did I ask you to specifically find where it went unstable? What did I say? What did I specifically say? Huh? Yeah, so just say Kp negative. If you make Kp negative, it'll go unstable. You can find where this happens, though, right? How would you find where this happens? You do round parallels, but you have the quadratic formula, don't you?
Yeah.
You said you get to one of the poles?
You set what equal to one of the poles?
The quadratic formula.
You set the quadratic formula. Equal to what?
Either -3 or -5.
-3, -5 are stable. I want unstable.
1.
I want it to be right when it crosses stability. 0. There you go. Okay? If you solve this, you get -8 plus or minus square root of 64 minus 415 plus Kp equals 0. You pull the 8 to the other side, and you square it. Squaring it gets rid of that plus minus. So you get 64 minus 415 plus Kp equals 64. Still with me? 64s will cancel. You get a, they don't actually cancel, my bad. If you pull 64 to the other side, you get a 0. So you get -4